Now to move on to our uncertainty in measurement. So, with every number comes an uncertainty in its value. But in chemistry, there are two types of numbers that we're going to use. The first being exact values. So those are going to be things like defined values. We know there are exactly 1,000 grams in 1 kilogram. We know that in 1 dozen there are exactly 12 objects. If you asked for a dozen donuts and only got 11, you would go back and ask for that 12th donut. Exact numbers are also determined by counting. There are 28 students in our class. I can't have a half a student. Can't have that. So there's exactly 28 students in our class. Inexact numbers are any number that is measured by any method other than counting. So that would be length, mass, volume, time, speed, anything else that you can measure. If we're dealing with an inexact number, then that inexact number must be reported to indicate its uncertainty. Since we don't know that number exactly, we usually designate our last digit as the uncertainty in that inexact value. So let's bring our sticks back, and now I have two different rulers that we're going to be using with these. So what I want you to do is measure the stick with each ruler. And of those two measurements, label your certain or your known digits, as well as your uncertain digit in that measurement. And then show me which digits are significant. Let's look at our first ruler here. This was the first one that we dealt with earlier when we said, maybe we said 4.5 centimeters, maybe we said 4.6 centimeters, okay? And we said it was kind of hard to tell if this stick fell exactly in the middle of 4 and 5 to know if it was 4.5 or 4.6. So our certain digit, I guess in this case, would be the 4. We are certain that this is more than 4 centimeters, but less than 5 centimeters. Our uncertain digit now is this final one, our first value after the decimal place, that is uncertain. We are uncertain of that last digit. But both of those values are significant to this measurement. Okay? I can't just say that the stick is 4 centimeters long just because I'm certain about the 4. I have to give that uncertainty. I have to give that estimated value in order to make sense of this stick and say, well, it's more than 4 centimeters, but it's less than 5 centimeters. Now, if we go to our second ruler here, the only difference is I have a few more tick marks on that ruler, so it's a little bit easier to measure. So again, we are certain that this is 4 point something centimeters. Now we can zoom in and say, okay, here's that 0.5. It's definitely greater than the 0.5, so I'm certain that this is going to be at least 4.5. But now I have to decide how far is it between that and its next tick mark. Could it be 4.55 centimeters? Maybe it's 4.57 centimeters. If it was perfectly on the line, maybe it would be 4.50 centimeters. That's unlikely since we know that it's not perfectly on the line here. I'll erase that to show it a little bit clearer. So we now have two certain digits. We are completely certain that this ruler is at least 4.5 centimeters. We then have to estimate our last value in order to get our full number. So we are uncertain about that last digit. But with that, all of our values are significant. So we can say here that we have 2 significant values. And here we have 3 significant values. So, which one of these 2 measurements that we just made has the smaller uncertainty? Has the smallest uncertainty? Which one are you more certain about? Take a second and think about that. Which one are you more certain about, or has the smallest amount of uncertainty? Because ruler B has more of these dashes in it, we can be more certain about the length of that ruler. Because we had 3 significant digits in the second ruler rather than 2. So we are more certain about our second ruler there. There's less uncertainty in that measurement. We know the length of that stick to more decimal places. Okay. So when I'm talking about these significant digits, we refer to those in chemistry and other sciences as the number of significant figures. So those are the numbers that are in our inexact values, where we have all of our certain digits, and the very last digit is our uncertain digit. But all of those digits are significant. So we can determine the number of significant figures in any given number, any given inexact number, using these guidelines. The first guideline is that any non-zero digit is significant. So we have the example here of 112.1. There are no zeros, so all of those digits are significant. So we have 1, 2, 3, 4 significant figures. When we have zeros between non-zero digits, then those zeros are significant. So if they fall in between non-zero digits, they are significant. So here I have 305. That has 1, 2, 3 significant figures. And 50.08 has 4 significant digits, 5, 0, 0, and 8. So in these numbers, these zeros fall in between non-zero digits, therefore they are significant. Our third guideline is that zeros to the left of the first non-zero digit are not significant. So we typically see this in decimals when we have really small values. So if they are to the left of our first non-zero digit, then they are not significant. So in 0.0023, these zeros are not significant. So my number only has 2 significant digits. In my second value, I have 5 zeros after my decimal, meaning those are not significant, and I only have 1 significant figure in that number. Our last 2 guidelines also have to deal with zeros. So when the zeros to the right of the last non-zero digit are significant, if a decimal place is present. So another way of saying this is if there are zeros after a decimal place at the very end, they are significant. So let me write that. Zeros after a decimal at the end. So we have the example of 1.200. So the 1 and 2, those are non-zero digits, and because these zeros come after that decimal place and they're at the very end of the number, they are significant. This would equate to if on our ruler we saw that it ended perfectly on a line, we would write it as 4.50. That 0 is telling us it is perfectly on the line. Therefore, it is significant to making that measurement, to knowing the value of that measurement. We need that 0 at the very end. Our last guideline is zeros to the right of the last non-zero digit in a number that does not, a typo there, that does not contain a decimal point, may or may not be significant. So this is the ambiguity rule, which we do everything in our power to avoid ambiguous numbers. So if we look at the number 100, okay, we don't have a decimal place, so we can't follow any of our other rules. These zeros then become unclear on if they are significant or not. So this number could have 1 significant digit, 2 significant digits, or 3 significant digits. So what we want to do is try to avoid being ambiguous. In order to do that, we are going to use scientific notation to express our values with proper significant figures. So if I wanted to express 100 having 1 significant digit, I would write it as 1 times 10 to the 2. Because if I were to write this out, that's still 100. It's still ambiguous if I write it not in scientific notation. If I wanted to show 100 with 2 significant digits, I would write it as 1.0 times 10 to the second. What happens here is this 1.0 now follows rule 4 that says because that 0 comes after the decimal place, I'll erase it so we can see it. Because that 0 comes after the decimal place, it is now significant. So I can say that the 1 and the 0 are both significant. The same goes for if we wanted to express 100 with 3 significant digits. I would write it as 1.00 times 10 to the 2. Again, these are all different versions of 100, just written in scientific notation, showing our different numbers of significant figures that avoid ambiguity, because that's our goal, is to avoid number 5, and it leads us back to number 4, to guideline number 4. So let's practice that a little bit. Let's go through these numbers and determine the number of significant figures in the following measurements. Okay, our first number is 443. Well, there are no zeros in that number, so we can assume that they are all significant. So this has 3 significant figures. Our next number is 15.03. That 0, this 0 right here, is in between non-zero digits. So this falls under rule 2, meaning that 0 is significant. So we have 1, 2, 3, 4 significant figures. The next number is 0.0356 kilograms. This is falling under rule 3, where the zeros to the left of our first non-zero digit are not significant. So these don't matter. Therefore, we have 1, 2, 3 significant figures. Next up, we have 3.00. 3.000, there we go, times 10 to the minus 7 liters. So this falls under Rule 4, where because these zeros are coming after the decimal place, they are still significant. So we have 1, 2, 3, 4 significant figures. Now I do want to make a comment because I oftentimes see students getting confused when we have numbers in scientific notation. They often ask, well, aren't those 7 digits there from the times 10 to the minus 7? Aren't they significant? Don't they matter? Well, if I were to try to write this number in non-scientific notation, which again, if you need a review of scientific notation, there is a portion of this video that will go through scientific notation. There's also an appendix in your textbook if you need a refresher. If I were to write this from scientific notation to its actual number, this would be 0.000003000. That is that number. So Rule 3 tells us that all of these zeros before our first non-zero digit are non-significant. So that's Rule 3. And then Rule 4 tells us that if the zeros come after a non-zero digit and it's at the end of the decimal place, they are significant. So even when I write it this way, it still has 4 significant figures. 1, 2, 3, 4. Our next number is 50 milliliters. This is one of those ambiguous numbers because we have this 0 at the end with no decimal present. So this could be, let's write it in red, 1 or 2 significant figures. We don't know, which is why we want to avoid ambiguity because it doesn't tell us a lot of information. Now in your ALEKS homework, I'm trying to write this over here, ALEKS wants you to add a decimal at the end of every number. Every whole number, I should say. Just to show if certain numbers are significant or not. Because 50, if I were to put a decimal there, that decimal then says that 0 is significant as well as the 5, so this is 2 sig figs. So by adding that decimal just at the very end, then that tells you that the numbers preceding that decimal are significant. It also wants you to add a decimal at the end of any whole number. So if we had our first number there, that 443, if that was your answer, it wants a decimal at the very end. Now this doesn't apply if your answer has to go into the decimal places. So if you had an answer like 15.03, then you wouldn't put an additional decimal place at the very end. That would be mathematically incorrect. So if you just have a whole number that you have to put in for your answer for ALEKS, it wants you to put a decimal at the very end. So just keep an eye on that when you're doing your ALEKS homeworks. Okay, our final example here. This falls under Rule 4, where I have this 0 at the end. Because that 0 is at the end after a decimal place, then it is significant. So I have 1, 2, 3, 4 significant figures. Let's check our answer key here. 3, 4, 3, 4, 1 or 2 and 4. Beautiful. Okay. Let's do some more practice. What I want you to do is pause the video real quick and try these on your own. Try going through these and identifying the rule that it falls under, and then how many significant figures it has. If it's ambiguous, write the ambiguous values, 1 or 2, 2 or 3. Our first number 23.45 has no zeros in it, so that falls under Rule 1. So this has 4 significant digits. Our next number, 23.057, falls under Rule 2. So this has 5 significant digits. That 0 is in between non-zero digits, therefore it is significant. Our next number, 230, is ambiguous, so this could be 2 or 3. We would need more information. Our next value is 231.0. Because that 0 comes after the decimal place, this falls under Rule 4. So this has 4 significant digits. Our next number has a 0 sandwiched in between 2 non-zero digits, meaning it is significant. So we have 3 significant figures. That is Rule 2. Next up, we have 0.00360. So this would be a combination of Rule 3 and 4 because these zeros before our first non-zero digit are not significant, but the 0 at the very end is. So we have 3 significant digits, 0, 6, and 3. Our second to last number has zeros that are sandwiched in, so we have Rule 2 again. So this would be 1, 2, 3, 4, 5, 6, 7 significant digits. And here we have a more ambiguous number. We don't have a decimal place anywhere, so this could be anywhere between 2 and 1, 2, 3, 4, 5, 6, 7 significant digits. We are very ambiguous on the sig figs of our last number. Okay, so how do we use significant digits specifically in measuring numbers? Well, we're in a chemistry class, so we need to think about how this applies to a laboratory setting. Even if you're not taking the laboratory right now, and you're taking it in a different semester, this still applies to what we're doing in this course as well. So, when we're taking measurements, say a volume of a liquid in the lab, we can only report those measured numbers to 1 decimal place further than the smallest measurement mark. So here I have a graduated cylinder. Which is a type of glassware used in a chemistry lab to measure volume of liquids. So we have our volume markings here. We have our major markings of by 5s. These are in milliliters. Okay, so these are milliliter values. And then we have 1 milliliter markings in between. So our smallest measurement mark in this graduated cylinder is 1 milliliter. And the rule is we can only report measured numbers to 1 decimal place further than our smallest measurement mark. So we can, our uncertain decimal, or our next place that we can go is 0.1 milliliters. So we have to measure it to the tenths place. Okay, so let's take a look at what we're measuring here for our liquid. So we know that we have surpassed 20 milliliters. We know our liquid line has surpassed 21 milliliters. So we are certain that this is at least 21 milliliters. Now because I've already guessed the tens and the ones place, I can only guess 1 decimal place further. So I can only guesstimate I can only guesstimate 1 more number. So we look at where this liquid falls in between those 2 lines because we know it's higher than 21 but lower than 22 milliliters. So we say it could be somewhere in between, like 21.5 milliliters. So of our options here, This first one doesn't work because I'm not measuring it. I'm missing a significant digit. I need my decimal place, so I only go to the ones place. In my third option, I go 2 spaces further than my smallest measurement mark, which I'm not able to do. I can't tell if that's 0.5 or 0.55. There's no way for me to tell. I only know that it is greater than 21 and less than 22 milliliters. So the only value that we can measure this to be is about 21.5. Now in the lab, you may not see it as 21.5. Maybe you see it as 21.7 or 21.4. That small amount of guessing, that estimation in the last decimal place, is where uncertainty comes from in the lab and why significant figures are so important. Because you may see it one way, someone else may see it the other. But as long as you both can agree that it is between 21 and 22, that estimation point in that last decimal place can be different. That's totally fine.